Okay, before we leave the topic on SDOF system, I would like to discuss to you the concepts of response spectrum analysis because this is very important in the analysis of structures, considering dynamic behavior. Okay, so first we define what response spectrum is. We have heard this a lot of times in a software presentation. So a response spectrum is simply a plot of the maximum response. And when we talk of response, we simply uh, are interested on displacement, velocity, and acceleration. As far as structural dynamic behavior is concerned, but any other quantity of interest may be used here in the definition, in the general definition of a response spectrum. So this again is a plot of the response versus a specified mode function, considering all possible single degree of freedom system, because we have to represent later the MDOF system in terms of the SDOF system for simplicity in calculation. So our basic requirement for creating or constructing a response spectrum is the SDOF system. So it can also be defined as a plot, a simple plot of the response versus frequency or period as your ordinate and abscissa respectively. Okay, so in figure 5.1 you have here an example of a response spectrum for a single degree of freedom subjected to a ground excitation. So if you have here a model, this is a building model or a shear building model. Okay, or a portal frame in which your response is actually observed, no, in terms of this graph here. Okay, so the displacement uh, response is actually uh, serves as the ordinate, while your frequency here, f, serves as your abscissa. No? Okay, frequency and period are actually related reciprocally by simply taking note that f is equal to 1 all over t. Okay, so in any case, in the later part of this discussion, we will notice that we will be using the period as your abscissa in favor of your frequency. So how do we construct a response spectrum? So the construction of a response spectrum may be done analytically and verified experimentally. Okay, so if we have here the analytical derivation or the analytical procedure on how to do it, we also have the experimental uh, procedure on how to check it. So we have to check whether your constructed spectrum is near to reality. Okay, so for analytical derivation, the procedure is similar to what we have discussed on the vibration concepts. Okay, so first we derive the differential equation of motion for the system, and then uh, we uh, we use the free body diagram, no, in order to derive the differential equation of motion. If the system is not yet converted into a mass spring dash pot system, so we have to convert it. And of course, considering the forcing functions f of t, which will actually dictate how your system will respond, we have to take note of the actual loading function. So in here, a loading function equivalent to a half a cycle sine wave. Okay, so this is a half cycle sine wave was used, and in a period or a duration of td. Okay, so d there means duration. Okay, consider now force and damped vibration. So the dm is as simple as writing down this force and damp uh, case. Okay, so this is your okay, so this is your force. Okay, this is your force and damp. Okay, case, and your forcing function is determined on the basis of an impulse load. Okay, so impulse loads are loads that are suddenly what stop at a certain time duration. Okay, so this is now a harmonic half cycle impulse load. Okay, sine wave. So your omega here is actually the same as your load frequency, capital omega, that we are using in our previous lecture. Fortunately, it was changed into a omega bar, so something like an omega with a bar on top. Okay, so the solution involves now a homogeneous and a particular solution. So you derive this in your advanced mathematics. So for this particular solution, it's a simple sine cosine function, and for the particular solution, it must be of the same form of the loading function. Okay, so this is also sine omega bar t. So where c may be obtained by substituting the particular solution to the DEM. If we substitute this as a solution to this DEM here, we can take now we can actually obtain the value of your coefficient c to be equal to this one. So I'd like you to recall your procedure on how to do it in advanced math. Okay, so this is advanced mathematics. Hence, the complete solution now will be the sum of the complementary solution or homogeneous solution. Okay, so let's call this now the complementary solution, or the homogeneous solution, and the particular solution UP. Okay, substituting zero initial conditions wherein the velocity and the displacement are zero, and solving for the constants of integration a and b, we can simplify further this complete solution into a specific solution in terms of F over K, where Fo is we know that this is the static displacement or deflection. Your omega bar is simply pi over the time of the time duration TD, and omega is simply equal to 2 pi all over the period T. Okay, so the time duration TD for an undamped vibration is actually half of the period T. Okay, so if we divide that, we can get as simple as pi over TD here. So kalahati nito is 2 pi, this is 2 TD, cancel that, you get a the same value. Okay, so omega bar is actually 2 pi over your period is 2 TD. Okay, so if you cancel this one here, it will now be the same as that. Oh. Okay, for your response now, we need to express it in terms of a ratio. Okay, this is sometimes called a normalized, okay, or dimensionless closed form solution. So we need to divide u and ust there. So we only take note of introducing, of course, these parameters here to eliminate Fo and K, and what remains here are functions of the time duration or the pulse duration Td and the time T. Of course, the period is also the basis for your response. Okay, so note that the response is a function of the pulse duration and time. So for a general arbitrary input load like wind and support motion like earthquake, we cannot obtain a response in this manner. No? So this is a closed form solution. It's an exact solution. Since your wave is defined in terms of a very harmonic periodic impulse loading, we obtain a closed form solution. So, but in case of arbitrary input loading, we cannot do that, no? So, what to do is to apply another procedure on analytically, and in doing so, we come up with what you call the Duhamel integral later, no? By the way, before I proceed, this is now the plot of this function here. So if I will plot both of this, okay, so this will be the result plot at t greater than td, meaning to say as it exceeds the value of the duration, it will actually have some what do you call this, abrupt, okay, discontinuous. Okay, so this is a abrupt change in the slope, or what you call discontinuity. Okay, so at this point where your time now exceeds the time duration TD. So impulsively dito matatapos yung forcing function mo, no? So somewhere here at TD over T equals 2.5. Okay? Okay. So for support excitation, wherein this is represented very well by earthquake motion, but not only earthquake, of course. So the free body diagram can be expressed as I have discussed you on the response to support motion. So we have what you call the absolute coordinates y and x. Now I use actually your u and us here. Okay, so u stands for the response absolute y, and us is the support coordinate. Okay, the movement of the support. So these are in absolute system. Okay, so if we take the free body diagram, so this is the same as the free body diagram I presented to you on the other video. So the equation of motion using the free body diagram can now be written in the form mu double dot plus cu dot minus us plus k quantity u minus u is equal to 0, or with the usual substitution of omega and the damping ratio. So this is the lambda, no? So this also the lambda that we are talking about in our previous lectures. So we note that your differential equation of motion can be written in this form. So u double dot plus 2 kasi omega u dot. Okay, so this Greek letter is pronounced as xi. Okay, so this is plus omega squared u is equal to omega squared us, a function of time. Okay, plus 2 times kasi omega u dot s function of time t. Okay, so this is now your transform equation coming from the basic DEM. So the above equation expressed in terms of the absolute coordinates in u and us, and in terms of relative coordinates, just like what we did in our support motion, we simply assume that your relative u is equal to y minus x, no? So this is just the counterpart on the change of variables concerned. Okay, so such that your equation now, by simply substituting the value of u is equal to ur plus us, we come up with your relative. Okay, we substitute ur plus us, the relative coordinate system, and the absolute coordinate system on the right side, representing the displacement brought about by the acceleration due to ground shaking. Okay, so this is your US. Okay, so this is again similar to a force damp oscillator, in which the solution is obtained by using the Duhamel integral series of impulse load lecture I gave you, the first batch of lecture I gave you last year, okay, last December. Okay, so for the Duhamel integral, all you need to do is to solve this numerically. If in case no solution can be obtained from an exact analytical derivation. Okay, so you can solve this using numerical methods. Okay, there are a lot of practical or experimental ways on how to plot also this, but you need a lot of instrument and a lot of recorded data to do it. Okay, so if you don't have the data, if you don't have the instrumentation, you cannot create a new response spectra for a particular uh, um, load function that you want to create. Okay, so but if you have the instruments, you have the lab And of course, this cannot be done overnight. You have to really compile, no, records on how on it. Okay, so before you can do it experimentally. So that's the biggest problem of response spectrum creation. So yun ang nagiging problema natin. Kaya uh, because this analytical graph must be verified yet by actual or experimental data. Okay, so that's it for the first part of the response spectrum. So I'll be continuing this on the next video.